Hello and welcome to this episode of That's Interesting. I'm your host, Frank Hart. This show explores things that I find interesting. I hope that you find them interesting too. In this episode, we will be talking with three members of the Quincy Robotics team, Hyper, robot number 69. With me are Chris Johnson, drive coach and mentor, and students Lilly Chen and Daniel Gladstone. Welcome to the show, Chris, Lilly, and Daniel.
Great to be here.
Okay. So to start off, why don't we start with Chris and introduce yourself and tell us your role on the project?
Absolutely. Yeah, I've been involved in the team since '98. It's almost 30 years now. I've been a mentor since 2006, and I do whatever needs to be done. This last year, I was the drive coach, so I was helping these fine students do the best they can during competition. But I was a electrical engineer, I was a mechanical engineer, I was a scout to try and figure out what the other robots on other teams were doing for several years. So, I've done all the things.
Yeah. Lilly?
This is actually my first year on this team or any high school robotics team ever, and I'm also a senior this year, so it's pretty late. I started as part of the mechanical team, helping build the robots, learning how things even worked together, because I came into this program not knowing anything about engineering. And then for this build season, for the 2026 first robotics competition, I was part of the drive team. I was the drive team lead and also one of two selected drivers.
Okay. Daniel?
I'm Daniel. I am a freshman at Quincy High. This is also my first year at robotics, and I spent most of the season on the control team, writing code. I did a little bit of electrical work, although I don't think you guys like the results too much, but they work. At the competitions, I was the technician, so if anything went wrong with the robot, I was the first person who saw it and had to think, oh goodness, what am I about to do?
Right.
Yeah.
Yeah. It's electronics, right? So, Chris, can we get a little bit of the history of the team?
Absolutely.
How far back does the team go?
So the team was founded in '96. Our original sponsor was AT&T. And then back in '98, when I first started with the team, our sponsor switched over to Gillette, and it was wild times back then because they didn't have any of the big rules that they have on the teams now, where it was basically there was no bumpers, there was no weight limits, you could do whatever you want in the robot. It was just like the Wild West, but it was so good. And like one of the things that's always been so good about the team is the exposure that the kids get to actual engineering, actual seeing a problem, working through it, building, testing, experiencing what it is and figuring it out in a setting where, it's not teachers teaching and students learning. It's like everybody is learning from everybody else, and it's like a peer environment. And over my years, I've seen so many kids that didn't know what a hammer was go to be very, very practical engineers, machinists, programmers, just wonderfully rounded people.
Right.
And actually right now on the team, all of the mentors, except for one, are people that had been students on the team at one point or another and came back, and they dedicate their time because it's such a good program and we're making the world a better place.
Yep. Yeah, it seems to be a lot of time gets spent by everybody involved with it to get
hundreds of hours.
I got to see a little bit of that work at the your test facility you build. It was impressive to see. It's really nice. Okay, so like any other project, has a development life cycle. So where do the requirements come from? What do they look like? So, Lilly, you want to take that? Can you take that?
Oh, the requirements? Do you mean like for each build season?
Yes.
So at the start of every season, there's typically two main ones. There's a smaller robot one called FTC, or like First Tech Challenge, and there's the FRC, which I mentioned earlier is the First Robotics Competition. So the first one is a smaller robot competition that spans from September to around December, and then the bigger robot competition is from around January to April, around. So at the start of every build season, we usually gather around as a team and watch the video that is released by First Robotics. And from then on, we would come together, think of some engineering ideas, do a lot of whiteboard discussions, say why this design works, why this design isn't as good. And then we just basically get to work with prototypes.
Yeah. Well, you've gotten us into the design phase now. So we have a couple of photos for design phase. Could we show the first one, please? Daniel, can you tell us about this one?
Yep, so this is one of the team members, Darwin. He's working on the on-shape model for the robot. The very first step, or at least the usual first step, before we actually start building robots and testing them out, writing code, is we make a model of them on Onshape or another 3D modeling platform. And this allows the engineers to see, okay, how do we place this here? What makes this work? How are we actually going to drive this mechanism? And all the questions that some of us, like I'm a programmer, I could not answer. Where are we going to put the battery? How is this wheel going to work? But the people who can figure that out, and they send all these models over to the people who are supposed to build the robot, and then we start work on the actual robot.
Okay. Can we get the next picture, please?
Do you mind if we go back to that one, actually?
Oh.
There's a couple of other things I wanted to
Okay, yeah.
mention.
There we
So
are.
one of the wonderful things about our team is we have such a huge space down in the basement of the church that we're in. And you can see in this picture, Darwin is working on that laptop there, but any team could do that anywhere. But the space is actually the fields, the size of the fields that the competition actually happens on. So we have this whole space here. So when we actually get the robot, we don't have to just build a small scaffolding to prove that it's going to do something in limited space. We can actually have the space to prove everything out the way we want to, and that's a real benefit for us. And in fact, a lot of times after the build season is almost over, we used to have other local teams like the Hingham team or the Weymouth team come over, and we would have this mini meet before we would actually go to competition. So they would get a chance to practice on our field, and we would get a chance to practice against other robots before it actually becomes serious. And the other thing I wanted to mention is if you see up at the top of the picture there, those are a lot of our old robots from back in the early 2000s.
Okay.
We don't really keep our old robots now. Most of the time the components are expensive, so we take them apart as soon as we're done with them. But these old robots, these are the ones that they've been around for 20 years.
Yeah.
I just like looking at them, and it's like a wonderful museum of where we came from.
Yeah, quite the history. Okay. Let's go to the next picture then.
So this is a very early prototype of our collector. So the way this year's game worked is that there's basically a bunch of small ball elements on the playing field, which are called fuel. And the objective of the game is to get as much as you can during the time periods where you're allowed to get those points into your fields, your team's collector. What's it called?
The hub?
Yes, the hub. So the way we designed our robot is to have a front collector that deployed, and then it would intake the fuel on the field, and then basically what this picture shows is how it would be moved inside the robot after it's taken in, and after all that it would be shot out into the hub. So this is the inner prototype.
Yeah. Maybe we should take a moment and just talk about the format of the competition itself. Like Lily was saying, and, jump in at any time. I've seen a couple of these because I watched them. So the robots, there's a lot of balls set up in the center between two sides, and red team is on one side, blue team is on the other side. They each have their hub that they throw balls into, and it works as the robots go out, they grab the balls, they bring them back to their side, they shoot them in. And this year I noticed that they have time periods where you can only score when your hub is active.
Yep.
So you'll see one side shooting the balls to get them into the hub, and the other team, the red team or the other team, the alliance, is going out gathering these balls, bringing them over to their side so that they can shoot them in. So, I mean, in my simple view, that's how this is working this year. So, sound reasonable?
Yeah, that's very accurate to the way that it was this year.
Okay.
This year, especially, they actually made it a point that a lot of the systems and the game components were stuff that they had used from previous years. It was like a 10-year anniversary of something where they just wanted to have like the way that they tried to frame it was like their artifacts of like the past coming together into this one game. And the only thing that was really truly novel this year was that timing thing that you were talking about, where you could only score in shifts, which made it so that like the strategy was, well, what do you want to focus on during your limited amount of time? Because each shift was only, 45 seconds?
25.
No, 25 seconds.
25 seconds?
It's been a minute. 25 seconds. So
it happens fast.
It does. It does. I mean, these guys know they were in the drive area when it was happening. So you need to decide, like, am I harvesting? Am I scoring? Or am I going to play defensive? Do I go over and I prevent other teams from collecting?
Right.
Because there's only a limited amount of fuel. So like a lot of that goes into the strategy, and like the wonderful thing about the drive team and the team in general is like they know the robot, they know themselves, they know the strategy so well that like drop of a hat, you can switch from saying, okay, we're going to be scoring as much as we can, or hey, that other team is doing too well, let's go like bump them right when they're shooting so they miss, and then if they miss all of them, then they have to wait another 25 seconds before they can score again. So it's a fascinating balance, and it gets really exciting when you're in the thick of it.
Yep. Yeah. I've watched a few of these like this year. I watched one in person in it happened to be at WPI.
Okay.
And then they're doing another one. My grandson's on the Westboro team, so I watch his. And they're doing another one first weekend in June at WPI, so I'll go out and watch that for a while.
Nice.
Yeah, it's fascinating to watch. Okay, so now we have the design done. Time to go in and start putting this whole thing together and making it work. So, build phase. We have some pictures for the build phase. So,
Sure.
Could we put up the first picture, please? Who's that standing there?
That is one of our mentors. I'm not sure if he's a regular, but he does show up sometimes.
Yep.
He is helping us in this picture basically figure out how to build the intake. Like I mentioned earlier, we have 3 main components of our robot. There's the intake to get the elements inside our robot, and then there's the inside spinner that organizes the elements that are inside to prepare them for the third phase, which is to shoot them into the hub. So this is our first step, the intake. As you can see, we decided on having 3 rods. Do you want to talk more about that?
Yeah, the way we designed it is on each side of the robot there were 2 pillars, and they would have teeth on them such that we could have one huge intake that could extend out of the robot. We could roll it out, and part of the challenge is you only get a certain amount of space for your robot. You can't build it too high, can't build it too far out, and you have to have bumpers on it. And we decided to make it so that we could roll it out such that when the robot's turned off before it starts matches, it could be inside its allotted spaces, and then the second we need it, we could deploy the collector right over the bumpers, and it would allow us to get balls without needing to worry about, okay, do we have a hole in our bumpers? Do we need to get these balls funneled in somehow? You could just deploy it over, and it would grab the balls, collect them, easy peasy.
Yeah.
Yeah, you can really see here the skeleton of how the design is coming together. So there's black sections on the corners. Those are the wheels. And each one of those wheels has 2 motors. One is to angle it, and the other one is to actually drive it. So the robot can actually go in any direction it wants.
Right.
at the drop of a hat. It makes it so that we're very, very powerful and we're very, very agile in our design. And this is sort of one of the standard sort of base configurations. You know, like the robotics has been around a long time. People figure out stuff, and then
Yeah.
that's the way it is. But yes, you can see the rollers in the front. That's the thing that's unique to ours. And like all of these pieces are stuff that we had kicking around, and then in these posts that are in the back there, some of that is actually 3D printed parts.
Oh, nice.
Yeah. So we have a wonderful, because of our space is so wonderful, we actually have a whole model shop, and we have a CNC machine.
Yeah.
We have a 3D printer. So very, very quickly we can get all the parts we want fairly quickly, and it's, again, to echo what I was saying before, it's really good for the kids because like these are the actual tools that engineers use nowadays.
Right.
So they get a lot of exposure to things that are very practical and very, real.
Yeah. Real life experience
Yeah.
with this is great. I
Yeah.
think it's terrific. Next photo, please.
So
Okay.
this is another part of our initial building phase. This right here is the third part I mentioned, the shooter, which is how we get the elements into the hub. From the very start, we debated between having a turret shooter, which could, it's just stationary and it could align itself like in whichever direction it's needed
Okay.
to shoot however far, however close, however like as powerful as we need to. However, our other choice was a double turret, which is in this picture right here. It's the one we eventually stuck to. Basically, compared to a turret, it cannot move itself. Whichever way the robot is facing is the way it will shoot. Yeah.
Yeah, you can see part of the design. Well, it's a bit hard to see, but these specific shooters, we designed them so we could have one huge flywheel on the left side, you'll see.
That's the big black thing in the front there.
Yeah, we have multiple motors spinning them up super fast so that when a ball goes through there, they get quickly accelerated and they're launched. And the white parts, they're actually a 3D printed hood. We have separate motors that allow us to adjust to the angle that they're shooting at. So depending on how far away the robot is from the hub, we can change how far forward or what the angle of shooting is. And it allows us to make much, much more accurate shots, although coding it was not as fun.
Yeah, to give people an idea, how high is the hub? This will give people an idea how fast these balls are coming out of there to get that. I'm going to, what are they, 10, 12 feet high, the hub?
No, the hub is only about, it's maybe, so it's like 4 feet.
Oh, about 4 feet.
Yeah.
Oh, okay.
But obviously you have to get the
Get it up and
angle
over,
going
yeah.
because you want to be able to shoot from anywhere. I mean, when we were shooting and we were still calibrating, the space in our church, we have ceilings that are probably 30 feet high, 25 maybe, and we were regularly bouncing it off of the ceiling.
Oh,
so
okay.
it was really like, it was going. But yeah. Actually, Daniel did a lot of the good angle calibration on the robot, because when you have it like that, you can't basically wait for lining the robot up by human eye, because
Yeah.
you're going to be at the driver's station back there. You're not going to be able to see exactly through what the robot's doing. So you have a camera on there, and the camera is always tracking exactly where the hub is. So it knows when you push a button, it's always going to align right to the hub, and then you shoot, and it's always going to know the distance away and
Yeah.
the angle, so it just gets right in, unless someone bumps you. And Daniel did most of the code for that.
Yeah.
Yeah, I started once we got the shooter. I tested different distances, so when I'm a few feet away from the hub, how fast do I have to have the shooter moving, or the flywheel in the shooter spinning, so that I could shoot the balls into the hub accurately. I'd move it this distance, I'd angle it a little bit, test out different configurations with the hood, and eventually, with the help of another mentor, Luke, who helped out with coding a lot, we were able to get a working automatic calculator that would, wherever the robot is on our side of the field, it would know the robot's angle, know how far away it is from the hub, tell the robot, you have to turn this much, angle the hood this high, roll up the shooters with this much power, and when all things go well, it shot in very accurately.
Yeah. We get the next picture, please.
So this is a very messy shot. This is how our development stages looked in the middle of the build season. So here we have a mentor and a senior student working on, I think, wiring.
We were trying to get everything connected to just see if we could get all the systems of the robot functional without needing to get it on the field and everything in working conditions so that we could drive it around. We just wired everything up, made sure all the connections were stable so we could test everything one by one on the bench. And later that wiring was changed.
Okay.
Yeah.
We have that same coding mentor loves to make sure the wires look clean so they didn't stay like this for long. But
Yeah.
Yeah. Now, one of the things you can see here, and like a lot of times, some people see pictures like this and they get a little like intimidated because it's like a lot of wires and a lot of motors, and but like, so that gray box that's up at the top there, that's the computer that controls the whole robot. And then right below it, all those little gold squares, those are fuses. So it's just like a fuse box in a house, where it's like if a motor is drawing too much power, it'll flip it, and you have to manually reset it. And it's so that the whole thing doesn't catch fire, because we've had that happen in the past, and we don't want a robot on fire. But yeah, you can see here all the components we were talking about previously. So there's the collector in front. The shooter is up here at the top here, and a little bit more of a configuration than we saw previously, with all the motors and the belts attached. We have the wheels, and then the thing that we saw prototyping before, the hop indexer with those spinning discs. You can see the aluminum discs we used just right there, as you know, inside this picture. So it really is starting to come together. And it always looks like a mess up until we go to competition, and then even when we get to competition, it's a mess.
Yeah.
It's a miracle we ever get anywhere.
Yeah. So let's go to the next picture, please.
I believe this picture is way earlier in the build season, because this is actually a robot from last year's
Oh, okay.
FRC, first robotics competition.
We can go on to the next one if you don't have anything else to say.
I can talk a little bit about how it worked.
Okay.
This one, I didn't get to see too much of its operation, but I heard general sentiment was it wasn't a great robot. But here's the elevator for it. It would raise up and down on rails. It would have that transparent polycarbonate sheet of plastic. You would put big rubber balls in there? Is that what the game piece was?
There were two game pieces. There was one that was like the size of a soccer ball, and then there was another that was like a PVC pipe. And you could only control one at a time. But the elevator here would extend up, and the idea was you're supposed to be like reseeding coral onto a reef. So there was this shelf that basically had all these PVC pipes sticking out of it, and what the elevator would do is it would allow it to go up, and then you could deposit the PVC pipes directly onto these posts that were standing on there. It was not as good as this year's design. The problem is it would go up and down okay, but if you were extended and then someone hit you, it would not go down okay again, and then you have this 50-pound weight in the air, and it was problematic. But that's one of the things that's really nice about the robotics program. Every year you have no idea what's going to happen. Like you start getting a sense of like, well, this last year we had balls that were like, you know, this big. So next year we're not going to have those. We're probably going to have like a big Pilates ball or some other. There was one year where it was basically those 3x2 crates, like the kinds that UPS uses.
Okay.
And we basically had to stack those and move them around. And it's like every year is different, but you never get the same components or the same elements 2 years in a row.
Yep.
So it makes it really interesting. Yeah.
So the next picture, we have the elements we're talking about, these yellow balls that they need to fly. So could we get the next picture, please? So is this in the collector, or?
This was one of the earlier photos. Before we actually build things out of metal, we always use plywood and other little scraps we have around. And this was a test for our spindexer and collector. And what we had a big box made of wood. That was where on the final robot, it would be something similar, but this was just a good demonstration to see how many balls could the collector collect, how many can it store. We would just attach everything to it, see how it fared, and all those yellow balls are the game pieces, all the fuel.
Okay. We have one more photo that shows the field, the playing field a little bit. So, can we get that photo, please?
Yes. So, as Chris mentioned earlier, our team is very lucky to have our own testing field, our own playing field, kind of in our build area. A lot of other teams I know don't have access to their own field, so they have to travel to other places often. They don't have much practice before actual competitions. So in this picture, students are assembling this year's game. And you can really see the scale of the field compared to the students, as in on the right, you see the hub, and that is just about how high up the fuel has to be launched in order to get points.
Yep. Okay. That's all we have for the build phase for pictures now. Any good stories about testing, like fires or shorts or?
What they told me a lot of times when I was testing out the shooter is, don't run it at full power. You will knock down ceiling tiles. And they have laser break fire alarms. They've done it in the past. If you launch a ball too hard, you will set off the fire alarm. And in testing, it was definitely fun seeing how powerful a shooter should be. But also, you have those times where just seeing what it could do in theory, how high you could go. And I'm yet to knock out a ceiling tile, yet to get my own souvenir.
But a couple years.
Yeah, it'll happen.
Yeah.
Yeah. Okay.
Yeah. I mean, it's the nice. There's so many nice things about robotics, but it's everybody is always there and putting in their time, and it always gets late, and people are always working, and like the kids usually get there right after school, but some of the mentors, they're working and they don't end up getting there until about 8 o'clock at night. So it's just, I can't think of any specific events that happened this year because it all sort of bleeds together after being part of something for 30 years. But it's always magical to like work on something where it's like one day you come in and you're like, well, this system isn't even together, and then you come in the next day and it feels like there wasn't any time at all, and they have a robot that's running on the field.
Right.
You're so excited to see it finally together because you're like, I only had this in my head or on the CAD drawings, and now it's like there it is, and you're like, well, that's not working and that's not working. But that's the fun of it. Like you finally get to that next phase and you're like, okay, we got to fix these things now too.
Yeah.
I remember another thing when we were a bit further, I believe around the time we're starting to write the code. I don't know who it was, but someone took the dev bots out for a joyride over the bumps on the field, and that was not a fun fix.
Yeah. So one of the things on the field this year is there were these bumps. They weren't too big. They were maybe a foot, maybe, but they had a bit of a steep angle to them. Yeah. And the old robots, the wheels were very, very close to the ground. So the problem is it would go up and over the bumps, and the whole underside would drag, and it would like tear off the underplate. And it was like they kept on saying, don't go over the bumps. And then of course one of the kids would just go over the bumps because it's fun to go over the bumps. And then all the engineers would just be glaring at them. They're rewiring it and fixing all the plating.
Yeah.
I don't know how many times in competitions, I couldn't count it, where the pit was telling me, tell the drivers to stop going over the bumps. They're destroying the robot. And I don't think I pressed against too
were you the driver putting them over the bumps?
Honestly, I try not to, because during the build season, everyone was just yelling at all the drivers, being like, never go over the bumps. But of course, there's this one mentor that kept being like, it's okay. He wanted to see the full potential.
Well, you have to really test it, right?
Yeah.
Okay, now we're going off to a competition. So we have about a 30-second video I want to show here that I cut out of each event's like about 3 minutes long.
Three and a half, I think.
3.5. Yeah. So I got 30 seconds out of it. So if we could play that video, please. If you want to talk about it, go right ahead.
There we are shooting and missing. Yeah, so there we are. This is when the hub is active and we can score in it.
And number 69 is the robot we should be watching.
Yeah. Actually, the other ones that also have blue bumpers, those are the ones on our alliance.
Right.
So when they score, we get points too. So that's.
Yeah. Well, let's talk about the format of the competitions now. Since we mentioned it, what's an alliance?
Mm-hmm.
So the way the game works is there's two alliances, the Red Alliance and the Blue Alliance, and ultimately the goal is to score the most points. Before the final matches, it's a little bit more complicated where you can still get points in different ways, but when you're in the final matches, it's just who can get the most points. And in each match, the Red Alliance has 3 different robots, and then the Blue Alliance has 3 different robots, and they all have to work together and compete against each other to make sure that their alliance is the one winning. And in that previous clip, you could actually see when our hub wasn't active, when the blue light wasn't on, we were shooting balls back into our area, making sure that we and our alliance members, when our hub was active, we could all use all the time shooting. And when it was active, we all have to make sure we can all shoot at once. A big part of our strategy was we sat in the trenches, and using our cool software aiming, we could sit there and shoot pretty accurately and let some of the other robots who needed to get closer up use that space.
Okay. Now, how are the alliances chosen? Are they
It's random.
random?
Yeah. So
So there are 2 main parts of each competition event. There's the qualification matches, and then there's the playoffs. So the qualification matches usually take around like 70% of the whole competition. It's where basically each team, as in like we're one team, Team 69, each team would try to get as many points during each qualification match to prove themselves so that during playoffs they get selected for an actual alliance.
Yeah.
So in the qualification matches, how it works is, as Chris mentioned, it's all randomized. You don't get to pick your teammates, and it's different every single match. So you get paired up with people you may have synergies with, people you may not agree with on some things, but you have to make it work either way. So there's typically like 60,
like that.
70 qualification matches.
Yep.
And then right after is usually a lunch break, or maybe a bit earlier, and then afterwards it would be alliance selection. So the way alliance selection works is the top 8? Yes, the top 8 teams, which they get their rankings from the qualification matches, how well they did, how many points they scored, how many matches they won. The top 8 after the qualification matches get to pick their own teammates. So I think how it works is if the first place team picked the second place team, then the second place team, if they accept, they would give up their teammate selection role.
yeah, and then the 9th seeded team
Right.
would become the 8th alliance.
Yep.
And how it works is that there's 2 selection phases. So the team leaders would first get to pick their first choice. It would go down the list. Second team would get to choose their first choice, etc. And then afterwards, it would be their second choice. And this year, I'm pretty sure there's only 3 teams on one alliance, compared to, I think last year, were there sub teams? Or
So they do things always a little differently every year. So what Lily's talking about is last year, every alliance was 4 teams, and the idea was if one of the robots was broken, you and your alliance could swap out for another robot, so that, because like the finals, it goes quick. Sometimes you have like 5-10 minutes from match to match. So if your robot breaks, you're done. So if you have another robot that you can pull in, it makes it a lot more dynamic.
Yep.
So, but yeah, they didn't have that again this year. This year it was just straight, 3 in an alliance.
Yeah, just wanted to mention too that, I mean, the robots show up like on Friday, and the alliances are all day Saturday, and most of all day Sunday. It's a long competition. It's not, a 2-hour football game or something. You're there for the whole weekend, and a lot of activity going on.
Yeah.
The first 30 seconds, remember? Autonomous control?
Yes.
Yeah. First 30 seconds.
And could you describe that, please? Since
So-
the program didn't?
The first 30 seconds of the game, the autonomous period, it's no people can be touching the controllers. You cannot control your robot at all, and all you can do is just set it on an autonomous mode. And what you do when you're programming the robot, you can create different autonomous modes which allow you to control the robot to set up predefined commands like move here, shoot here, turn here. And the beauty of it is you can get super high point counts in autonomous mode since nobody can react to any sudden movements you make. But in return, you have to think of those genius strategies. What if I did this? That would get me to these balls faster than the other team.
Yeah.
I could take them all, shoot them all. And you have to work with your teammates because going over the bump, it could damage your robot, but it's a very fast way to get around. And if two teams want to use the same bump, one has to have either a different auto that they can use, or they have to figure out, okay, if I do this, we can have our robot start just a bit off the center so that it'll move here instead. And all that strategy goes down in that autonomous period. The goal is still to shoot as many balls as you can, but since it's the very beginning of the game, everything's in order, you know where everything is. You can create predictable routines you can run over and over again. And the autonomous period, it's a huge source of points, but also it determines how the rest of the game goes. If your alliance scores more points than the other alliance in the autonomous period, then that other team, the team that's currently lagging behind, would get to start off with their hub active, so they immediately get to start shooting balls. And you and your alliance have to prepare, and then it continues with the rest of the game flow.
Okay.
And programming it's difficult since when you don't have control of the robot, if it makes a mistake, you have to be on top of it, know what to fix.
Yeah.
If it starts driving into a wall, you have to stop it immediately or else it starts damaging things. I think I was a pretty good source of wood chips on the field.
Yeah.
So then it goes into driver control. So having a driver here, Lily.
Yes, so driver controls, every year we have a different setup, kind of. We reused, what was it, a console controller, as in like the video games controllers you see. So we simplified it a lot this year. Instead of having two drivers playing simultaneously, like for example, last year we had one that was just controlling how the robot moved, and then the other driver would be controlling how the robot operated, which is like, as you saw earlier, there were a bunch of elevators that had to extend all the way up, had to put the pipes on the shelves. So that driver would be controlling like when it extended up, how far it extended up, and how it just moved, other than how it drove around. So this year we just had one person take care of everything, and that person basically had to know where to go, how fast to go, when to rotate, how fast to rotate, and also when to wind up to start shooting, and when to actually shoot, when to position yourself, press the one button that positioned the robot towards the hub, like we mentioned earlier. We have a camera system that does that automatically. Yeah, and our setup was basically that controller hooked up to a laptop, and the laptop would show a driver station, which just showed the countdown and basically which parts of the robot were active.
Okay.
So for example, there were a couple of matches where everything was red on the screen, which meant that we couldn't drive it at all because all the systems were offline. So that's basically how we keep track of the robot while still being behind the glass, looking into the playing field.
Okay. We have a couple of pictures. Can we get the next one?
So that's me on the left in our signature team gear this year, which is the flower lays. Here we are in the pit, which is the working area for when we are between matches. It's where we first set up our equipment, all our tools, and where we store our robot at first. And you can also see the cart that we built for this competition this year, which the robot is on the cart. And also the tray you see in the front, that's the physical driver station that we carry to, what's it called? Behind the glass, where we set everything
driver
down.
station?
Yes,
Yeah.
everything's called a driver station. It's confusing.
Driver control in the driver station.
Yes. So as you can see, the controller is hooked up to the laptop, and the laptop is attached to the physical driver station. So it's harder to just drop and like let everything slide down when we're moving them. And basically, I think we're between matches here. We have a mentor fixing the robot. I'm assuming it's the intake because that broke a lot.
Always is the intake.
And I am basically reviewing the controls here.
Okay.
A big part of making sure the robot's ready for matches is, well, I can talk about the area first. This is the pit area. It's where all the robots go in between their matches, after matches, before matches. Any fixing that needs to be done, anything with the robot that you can't do on the field, anything at all, that's where it gets done here. And then the robot goes to the competition area where you're actually playing the matches. But here, the pit's job is to make sure the robot's ready to go, nothing's broken, and to make sure that we actually get out to our match on time. And an important thing that we have to do is before we go out every single time, we have to do what we call a bench test. We have to check every single control, make sure nothing's broken, because the second we leave the pit, it gets 10 times harder to fix anything on the robot. And knowing the controls, you always have to know the controls.
And the battery.
Oh, the battery. Yeah.
The battery is only a car battery, and these things take a lot of power. So
Yeah.
if you don't swap out the battery before every match, what happens is you'll go into a match and you'll sort of run out of power
Okay.
halfway in, and we don't want that. So it's
Right.
like every match you have to swap out the battery first.
And I believe there's one more picture.
So this was during our first competition. We went to 2 this build season this year. This was in the last few matches, and here you can see us with our alliance. What alliance number were we on? I think 5.
Sounds right.
Yes.
Yeah.
So we were selected to be the second choice of alliance number 5. There's 8 total. And our team captain, you can see on the left, that's one of the team members that's gone fishing. And then we have the yellow shirt team members, that is Ozram. And basically we're just celebrating because it was honestly a miracle that we won up to round 5. I think after round 5 is semifinals, right?
Yeah.
So it was honestly we were really happy that we got up to all that. Yeah.
Was this after our match that we beat, what was it, Alliance 2? Or one of the really, really powerful alliances? We were able to beat them, and it was absolutely crazy because the way the alliance selection worked is generally the higher alliances will have more powerful teams, and when they're all bunched up together, the lower numbered alliances, they can really easily get knocked out straight out of the competition. And I remember the first competition, we managed, as the underdogs, we managed to beat a really, really, really powerful alliance, and I think that photo was taken right after that. We were all super excited celebrating because we were all prepared going into that match thinking it was going to be our funeral, and we came out victorious, and it was best feeling.
Oh, yeah. So is the season over now?
Yes.
Yeah.
Yeah. There's still one competition we're going to go to in the fall,
Okay.
but it's not an actual first robotics competition. I think it's going to be out in. Is that the one in Worcester? Or is that the one at WPI? It doesn't matter. Basically, it happens in the fall, so we
Yep.
use it as a good excuse to get the new kids starting the new school year to get excited, come to a competition, see what it's all about before they actually
Yeah.
need to. And we'll have the Lily won't be there unfortunately, but Daniel will be there, and the rest of the people will be there, and we'll take the old robot and we'll go out and we'll spend a day of it and
Nice, yeah.
get kids excited about robots.
That sounds good.
Yeah.
So earlier you mentioned sponsors, Chris. So
Yep.
just wanted to talk about your sponsors a little bit.
Yeah, sure.
And maybe fundraising, and do you accept donations?
Absolutely. Yes. So let me talk about those in stages.
Yep.
So we always need money. So building a robot like this is fairly expensive. Like all told, going to competition, getting all the spare parts, getting the robot together, I think it's something like 10 to 15 grand. So we're very lucky. The Quincy Public School really supports us. They give us free rein to run the program the way we see fit, because they know that we're all engineers who really care about the program and really want to make sure that the kids get the best education possible. Right now, our main sponsor is Granite Electric, who what do they do? They do, is it routers that they build? Electrical switches, I think.
Okay.
I could be wrong. I'm sorry. If that's factually incorrect, cut it. I don't want to say something bad about it. They've done a good job helping us with fundraising. The other thing we have is several years ago, I want to say it was like 2010, 2014, something like that. We knew we were always going to need money for the team, and we had all of these kids who had graduated and really, really cared about the program, but they couldn't donate time. So we created a nonprofit organization called the Hyper Alumni Association, and it's a fully 401c3 nonprofit organization. And a couple of times a year we do fundraisers, but we'll always take donations. And the mentors that we come, they don't just give time, they give money.
Yep.
And that's the only way that we make the whole thing work. So yeah, if anyone wants to go and donate some money to the Hyper Alumni Association, we'll put a good use, and if you donate enough money, we'll put your name on the robot.
I will try to add the
URL?
URL
Yeah.
for that, so if you could send it to me, we can do
Yeah,
that.
absolutely.
Or I'll try to find it, but
Yeah,
either
yeah.
way. Well, I think that's pretty much everything that I have.
Yeah.
Did I miss anything, or? No?
No, it's just a great program. Great kids.
Okay.
Yeah.
Yeah. No, that was very impressive,
Yeah.
what I saw.
Yeah.
Okay. So we're now at the end of this episode, and I want to thank my guests, Lilly Chen, Daniel Gladstone, and Chris Johnson. Thank you for watching this episode, and I hope that you stay interested.